Okay, let's look at this question number 1 from the class example set. You have two objects and they're moving with different accelerations, and pardon my typo in your actual handout, I left out the squared for the 4 meters per second squared and the 6 meters per second squared. Let's look at this first as a velocity time graph. So I think that if we do that, it might help. Okay, so the cycle has a greater acceleration, but just for a shorter amount of time, because it's going to stop accelerating once it reaches 9 meters per second. So that may look like our 9 meters per second. So this is our cycle. Okay, but the car has a lower acceleration, but for a longer amount of time, because it's going to reach a velocity of, this is not drawn to scale at all, but 22 meters per second. Okay, and then it's going to move at a constant speed there. Okay, so this is the car. Now the idea is that we're looking for when are they at the same place at the same time. Now displacement is the area under the curve, or the area under the graph. So for the cycle, when will the area under this green graph be the same as the area under the blue line? Okay, so I'm going to go all the way down. So when will those areas be the same is what we're looking for. So we're looking for this time, t. Now I have arbitrarily chosen that time to be before the car stops accelerating, so before it reaches 22 meters per second. And there's a couple ways that we can work on figuring out where that is. So first of all, the cycle definitely has this first area right here that is a triangle. Okay, and it has the second area that is a rectangle. Okay, so let's say that our change in position for the cycle has to be equal to the change in position for the car. Okay, and that is the area under the graph for the cycle has to be equal to the area under the graph for the car. Now the cycle has two portions, a triangle portion and a rectangle portion. Okay, so for the triangle portion, we have 1/2 base, which I don't know what that is. I'll label it T1 for now, times the height, which is 9, 1/2 base times height, plus base T minus T1 times height of 9 has to be equal to the change in position for the car, which will be 1/2 base T, okay, that time right there, times height, which is some final velocity that I don't know. So those have to be equal to each other. There are a lot of crazy unknowns there, but I can figure out some of that stuff. So let's figure out, well, what time does the cycle stop accelerating? So we'll start with that. So if V is equal to V naught plus AT, so that's the equation of that line, my final velocity is 9, my initial velocity is 0, my acceleration was 6 meters per second times t. The time it's going to stop accelerating is 1.5 seconds. Okay? So now I have a time to put in for this portion right here. I'll have a time for this portion right here too. Okay, so let's do a substitution down here. 1/2 1.5 times 9 plus final t minus 1.5 times 9 is equal to 1/2 final time times final velocity. Because I don't know the speed of the car, okay, at that point. Now, I could use the equation of the line to find that speed. So, what is the speed of the car at t? So if v for the car is equal to v naught for the car plus at for the car, the final velocity is unknown. The initial velocity of the car is 0, okay? Because we're looking at this time interval right here, okay? Plus the acceleration of the car is 4. The time that from when it starts to the time when they meet is t as defined by my graph. So now I can substitute 4t into the equation for, so it'll go 4t can go in right, boop, right there. Okay. So now let's see. We'll have 1/2 1.5 times 9 plus final t minus the initial t, I'm just writing what I've got up here down again, is equal to 1/2 t times 4t, so that would be 4t squared. Okay? So this is 6.75 plus, alright, I'm going to FOIL this out, so I have 9t minus 9 times 1.5, which is 13.5, is equal to half of 4 is 2t squared. Alright, so now we've got this quadratic equation. Let's see, so negative 2t squared plus 9t minus 6.75 minus 13.5 is negative 6.75. That equals 0. And then solving the quadratic equation, you should get 3.55 seconds. And then you can check to see that that works. And that's probably the most conceptual way to solve that problem. Now, equation-wise, if we look at delta x for the cycle is equal to delta x for the car, and I think about it in its steps, delta x would be equal to v naught t plus 1/2 at squared during the acceleration portion, plus position is equal to v naught t plus 1/2 at squared for the non-accelerated portion. So this is when a is equal to 6 meters per second squared for the cycle, and this is when a is equal to 0 for the cycle. And that would have to equal the area under the graph, or the change in position for the car, which would be v naught t plus 1/2 at squared, and this acceleration was given as 6. So here, when it's accelerating, the initial velocity was 0, So this would be 1/2 6 times t1 squared for the time that it was accelerating, plus, now that it's not accelerating, we have its final velocity for the acceleration portion is the initial velocity for the constant velocity portion. Sorry, we were given that. That would be 9 times t, meaning the time that it's moving at a constant rate. And that would be equal to, our initial velocity for the car is 0 plus 1/2. Its acceleration is 4. I'm going to call that t1. Nope, plain t. Sorry about that. T squared. Now I have two unknowns here, so I need to figure out what time does this guy stop accelerating. So we need to find this guy right here. I can find the time that it stops accelerating by using v equals v naught plus at. So that is the final velocity of the cycle was 9 equal to 0 plus 6t. Therefore, time is 1.5 seconds there. So that's the time that it is accelerating. So make a substitution. 1/2 6 times 1.5 squared plus 9t is equal to 2t squared. And this should give us negative 2t squared plus 9t, and this should be negative 6.75. And again, solve the quadratic. And I believe you will get again 3.55 seconds. Okay? I like the graph much better, but either works.